Welcome to the deep dive. If you've ever watched a weather forecast miss a localized thunderstorm by like 3 blocks,
Mm.
just how incredibly hard it is to model precipitation accurately.
Oh, absolutely. And today we're digging into some really fascinating research that's trying to change that.
Right. It aims to fundamentally rethink how we reconstruct rainfall patterns,
hmm
moving way beyond just measuring to actually understanding the storm's physics and structure.
Exactly. This is all about the critical need for high-resolution rainfall data. I mean, when we talk weather prediction, people often focus on the forecast itself, but the bedrock, the foundation, that's
Mhm.
accurate data, historical and near real time.
And you need that detailed data for so many downstream applications.
For everything. Infrastructure design, like city drainage, setting up effective flood alerts, even modeling how climate change impacts local water resources. You need to know precisely where and how much rain fell.
And the consequences of getting this wrong aren't just theoretical.
Yeah.
They could be absolutely devastating. Our sources point to the 2021 Eifel floods in Germany. Just a horrifying example.
It really was. The core issue there, a significant factor at least, was that the storm center was badly mislocated in the initial assessments.
Likely because of distortions or maybe over-smoothing from the existing sensor networks.
That seems to be the case. And that mislocation delayed critical life-saving alerts.
The result was just catastrophic.
Unbelievably so. 243 people lost their lives, and economic damage was, what, over 46 billion euros?
Yeah. That disaster didn't just highlight a data gap. It really exposed a fundamental failure in how we resolve the spatial details of intense weather.
Definitely.
And that failure brings us straight to the problem this research tackles head-on.
Mm.
Currently, we mostly rely on these sparse networks of automatic weather stations, right? AWS.
Yep, those ground stations. And then we basically try to guess what's happening in between them using statistical methods.
Like creaking or inverse distance weighting, IDW. Filling in the blanks.
And there's the rub. Those methods, they inherently assume spatial smoothness. They draw like a gentle curve between two distant points.
But intense rainfall, especially the kind causing flash floods, is anything but smooth.
Exactly. It's characterized by sharp edges, super localized extremes, things like convective cores. If your method inherently smooths out those dangerous details, your understanding and any forecast built on it is already flawed from the start.
Okay, so the mission here is to introduce a new framework called RainSeer. It's designed to be structure-aware.
That's the key term.
And the core idea isn't just, more data, but reinterpreting radar reflectivity, what the radar actually sees as a physically grounded structural prior.
Precisely. It's about using the storm's anatomy, its structure, to guide where the rain must have fallen, shifting the focus from just where's the strongest radar signal to actually modeling when, where, and how the rain develops based on the physical rules you can see in the radar patterns.
Let's unpack that a bit more, because that distinction feels really important. We often hear rainfall is far from uniform, but what does that variability really mean when you've only got a sparse AWS network?
It means those networks are essentially blind to the most dangerous localized events. Imagine trying to map a really complex mountain range, but you only have, say, 5 elevation markers scattered over a massive area.
You get the general slope, maybe?
Right, the general slope, but you totally miss the sudden cliffs, the deep, narrow canyons, the isolated peaks. It's the same with rain. If your gauges are 50 kilometers apart, you are definitely going to miss that hyper-localized downpour that floods one specific valley or town.
So the traditional ground-based methods, they just can't capture those extremes because they rely on those few points and assume smoothness. What about remote sensing then? Satellites, radar, they give you better coverage, don't they?
They absolutely give you wider coverage, yes. Satellites and radar see large areas, but they often map precipitation as kind of spatially uniform blobs within large grid cells, or they really struggle with accurate intensity calibration at the surface.
But the opportunity lies in the radar data itself.
Yes, because radar data is incredibly rich. It's not just a flat picture of where it might be raining.
You said earlier it's like a dynamic scan of the storm's anatomy.
Exactly like that. It encodes the storm's physics in real time. For instance, if you see really deep echotops reaching high into the atmosphere, that hints at powerful updrafts, potentially carrying hail, very specific high-impact precipitation.
Okay.
Or you see bow echoes in the radar structure. That traces damaging straight-line winds, Hook echoes famously show rotating mesocyclones, potential tornado precursors.
These are just random shapes.
Not at all. They reflect the physical processes organizing the storm. They tell you how the storm is built and where the intense rain is most likely to be concentrated. We need a system that learns to read those specific structural clues.
That sounds incredibly powerful. But it also sounds technically really challenging. You immediately run into problems trying to use radar that way. The research mentions two fundamental disconnects RainSeer had to tackle.
Yeah, two core challenges. Let's call them C1 and C2.
Okay, what's C1? The spatial resolution mismatch.
That's it. C1 is all about the massive difference in the type and scale of the data. On one side, you have radar giving you these detailed volumetric scans, full 3D pictures of the storm structure, the powers, the bands, down to maybe kilometer scale detail.
So a dense 3D moving picture.
Right. And you're trying to match that with, what, a handful of static point-based measurements from AWS stations sitting on the ground.
Just single points, far apart.
Exactly. The gap in scale and dimensionality and sampling density is just enormous. You're trying to map this rich volumetric field onto sparse points. It's what mathematicians call an ill-posed problem.
Meaning there's no single obvious solution.
Right. There are countless ways you could theoretically fill the space between the AWS points using the radar info. Getting the one physically correct answer is incredibly difficult without some very smart constraints.
Okay, that's the structural alignment problem, the scale mismatch, C1. But hang on, even if you could perfectly line up the 3D radar shapes with the ground points, isn't there still a problem? Radar sees what's up high, not what actually splashes on the pavement. What's the second challenge, C2? The physics one.
That's challenge 2, semantic misalignment. This one's purely about the microphysics, what happens to precipitation as it falls. Radar senses hydrometeors, that's ice crystals, cloud droplets, raindrops suspended aloft in the cloud.
Way up there.
Yeah. But the AWS gauge, it records only what manages to survive the journey and reach the ground. And a lot can happen on that journey down.
Like specifically, besides just falling.
Well, first, wind. Wind drift or advection can blow the falling rain sideways, so it lands quite far from the radar echo core you saw directly above. That's a spatial shift.
Okay, so it doesn't fall straight down.
Often not. But maybe even more critical is intensity ambiguity. A really strong radar echo high up doesn't always mean heavy rain on the ground.
Why not?
Evaporation. If the air below the cloud is very dry, that intense signal you saw aloft could be rain that evaporates completely before it hits the ground. We call that virga.
Ah, right. You see the streaks, but nothing reaches you.
Exactly. Conversely, if ice particles or hail are falling and they melt on the way down, that dramatically changes their size, shape, and how they reflect radar signals, and it adds water mass. So a single radar reflectivity value aloft could mean anything from light drizzle to virga to melting hail by the time it reaches the surface. It depends entirely on the thermodynamics below the cloud.
So the system can't just naively assume bright echo equals heavy rain. It has to learn to interpret the signal in context, filtering out the virga, accounting for melting, wind drift.
It has to learn the physics of descent.
Which brings us neatly to RainSeer's architecture. It's this two-stage, physics-informed setup designed specifically to tackle C1 and C2. How did they use AI to bridge these gaps?
It's quite elegant, actually. The two stages directly map onto the two challenges. Stage 1 is the structure-to-point mapper. Its job is to handle C1, that big spatial scale and alignment mismatch we talked about.
Okay, how does it take that complex 3D radar structure and relate it meaningfully to those sparse points on the ground?
It uses what they call hierarchical multimodal encoders, fancy term, but basically you have one encoder, a radar encoder, that processes the radar data to understand the storm structures. And you have another, an AWS encoder, that handles the sparse ground station data.
How does the AWS encoder handle sparse? That seems like the hard part.
It uses graph attention networks, or GATs. GATs are really good at finding relationships in sparse, irregularly spaced data, like a weather station network. And they do something clever. They actually use the radar data nearby to create virtual nodes.
Virtual nodes,
Yeah.
like imaginary weather stations.
Sort of. They're interpolated points based on the radar field, placed strategically where there aren't real gauges. It helps the GAT better understand the spatial patterns and correlations, even in areas with no direct measurements. It makes a sparse network feel a bit less sparse to the model.
That is clever. Using the radar to effectively densify the ground network for the AI. But how do they actually align the processed radar structure with the processed ground data? That seems crucial.
That's the job of the core alignment module, the cross-scale aligner. It uses something called bidirectional physics-aware attention, or BPA-MHA. The key word there is bidirectional.
Bidirectional, meaning it looks both ways.
Exactly. Most systems might just do radar to AWS attention. That means asking, how does the storm structure I see in the radar influence the rain measured at this AWS station?
Makes sense.
But RainSeer also does AWS to radar attention. It asks the reverse. How does this trustworthy ground measurement I have from the AWS station inform or correct my interpretation of the radar structure?
So the ground truth gets to provide feedback to the radar interpretation.
Precisely. It forces the model's understanding of the 3D storm structure to be consistent with what actually happened at the surface. It's a feedback loop that anchors the radar data in reality and achieves that crucial spatial coherence. It's a really key innovation for tackling C1.
Okay, that sounds like a solid solution for the structural alignment for C1. Now, what about C2, the semantic challenge? The problem of virga, melting, wind drift, all that microphysics. How does the second stage handle that?
That's the role of component 2, the Geo-Aware Rain Decoder. This part is explicitly designed to model those downstream physical processes, the descent, the potential melting or evaporation that determine the final amount of precipitation reaching the ground.
And how does it model those complex, often very localized processes?
It uses another specialized attention mechanism called Causal Spatiotemporal Attention, or CSTA.
Causal, again, that word seems really important here. It's not just finding correlations in time, it's finding cause and effect.
That's exactly the idea. The CSTA essentially acts as a learnable filter, or a structural prior, that enforces physical plausibility over time. It looks back at the sequence of radar signals observed above a location.
Okay.
And it implicitly asks, which parts of the radar signal I saw, say, 5, 10, 15 minutes ago, actually had a causal link to the rain I'm seeing on the ground now?
So if a strong radar echo appeared aloft, but then led to no rain at the surface, maybe it was virga that the system learns to downweight that signal.
Precisely. It learns to focus only on the historical radar features that have a demonstrable causal influence on the surface precipitation being measured or predicted. It filters out the misleading signals, like evaporating rain streaks.
Wow, so it's essentially learning the microphysics of precipitation descent by observing cause and effect over time in the data. That's a very clever way to bake physics into the AI's attention.
It ensures the predictions are not just statistically correlated, but also physically plausible and temporally coherent. It helps avoid the common problem in simpler models of overestimating rainfall based just on strong radar echoes aloft.
Okay, this architecture sounds really well thought out, directly targeting the known problems. Let's talk results. How did RainSeer actually perform when they put it to the test against real-world data?
They did a pretty robust evaluation, which is crucial. They used 2 very different datasets to check if the approach generalizes. First was RainF from South Korea.
What's characteristic of that one?
It's dominated by intense, often very complex, fast-moving convective storms, the kind that cause flash floods. Real stress test.
Okay, and the second?
Medionet from France. This dataset features more stable, large-scale, often lighter precipitation patterns, so 2 quite different rainfall regimes.
Good contrast. And how did RainSeer do compared to, say, the standard methods like Kriging or even other deep learning approaches?
It showed really consistent and pretty significant improvements across the board on all the standard metrics.
Like mean absolute error, MAE.
Yep. Overall, RainSeer reduced MAE by over 13.31% compared to the best baseline. But here's the really striking part. On that challenging RainF dataset, the one with intense convection where traditional methods really struggle,
Yeah.
RainSeer cut the MAE by a massive 70.71%.
70%. A 70% reduction in error for those dangerous storms. That's, wow. That strongly validates the structure-aware approach, doesn't it?
It really does. It shows the benefit of understanding the storm's anatomy. And it wasn't just about getting the amounts right.
What about the pattern, the shape, the sharp edges?
That's where the correlation coefficient, CC, comes in. It measures how well the pattern matches the ground truth. RainSeer boosted CC by over 10% on both datasets, 11.15% on Medionet, 10.48% on RainF.
So the reconstructed rainfall maps weren't just more accurate in total volume. They actually put the intense cores and the sharp transitions in the right places.
Exactly. Better structural fidelity. Closer to reality.
Let's dig into the ablation studies. That's where they take pieces of the model away to see what breaks, right? To understand what parts are truly essential. What did they find was the absolute cornerstone?
Unsurprisingly, perhaps, it was the radar input. When they removed the radar data entirely, relying just on interpolating the AWS stations,
Performance plummeted.
massively, substantial degradation, as they put it. For instance, a key metric used in hydrology, the Nash-Sutcliffe efficiency, or NSE, which measures predictive skill, dropped by over 65% on MediaNet.
Okay, so that confirms it. You absolutely need the radar for the structural information. It prevents the AI from just defaulting to that overly smooth interpolation.
Right. Radar provides the essential physical structure.
But what about the other side? If radar provides the structure, what was the role of those sparse AWS ground measurements? Could the sophisticated AI have maybe just learned from the radar alone?
Nope. And this is another really important finding. When they removed the AWS input, relying only on radar, the error also increased significantly.
Why? What did those few ground points provide?
They provide the essential intensity calibration. They act as the ground truth anchor. Even sparse, those AWS measurements are trustworthy points of reference that stop the model from just running away with the radar signals and maybe consistently over or underestimating the actual rainfall amounts. They ground the whole system in reality.
So it's not radar or AWS, it's the intelligent fusion of both that's key.
It's the synergy, yes. And the ablation study also confirmed that the specific architectural components designed for that synergy, the bidirectional attention, the causal attention, were critical. Removing them hurt performance because the model lost its specialized ability to align the scales or filter the signals physically.
Makes sense. Before we wrap up, I wanted to touch on one more detail they mentioned, using something called geo-loss during training. It sounds simple, but maybe quite effective.
Yeah, geo-loss is a neat touch. It's basically a regularization term added to the training objective. It's rooted in a very fundamental idea in geography.
Yeah.
Tobler's first law of geography. Sounds grand, but it's beautifully simple. Everything is related to everything else, but near things are more related than distant things.
Obvious when you say it, I guess. How does that apply here?
In practice, geo-loss penalizes the model if it gives too much weight to information from a very distant weather station compared to a nearby one when making a prediction for a specific point.
So it encourages the AI to trust local information more.
Exactly. It pushes the reconstructed rainfall field to be spatially consistent, ensuring that the conditions at a specific location, primarily understood through the local radar structure, are primarily calibrated by the nearest, most relevant ground truth measurements, not distorted by data from hundreds of kilometers away.
That combination of sophisticated AI like causal attention with fundamental geographic common sense, that feels like the real step change here.
I think it is. RainSeer represents a shift, moving away from treating radar as just another data layer to be blended in somehow. It elevates radar to be a dynamic, physically structured prior that actively guides the reconstruction.
And the outcome is the ability to recover fine-grained rainfall much more accurately, especially, as the case study showed, during those abrupt changes or near-intense features where older methods tend to blur or misplace things. RainSeer's maps just looked much closer to the observations.
That capability, that high-fidelity recovery, especially for the challenging convective storms, is what can genuinely improve things like flash flood warnings and water resource management. It moves the needle on resilience.
Absolutely. And applying causal inference to model these dynamic physical processes like melting and evaporation. That seems really powerful. So here's a final thought for you, the listener, to chew on. If we can use this kind of physics-grounded, causally aware AI to predict something as complex and fast-changing as precipitation evolution with this level of fidelity, what other complex dynamic Earth systems are maybe on the cusp of being understood and modeled this way? Think about ocean currents, wildfire spread, maybe even things like volcanic ash plumes or subterranean water flow.
Yeah.
Could this approach, blending AI with physical and causal reasoning, unlock a new level of accuracy and interpretability for predicting those systems too, ultimately building unprecedented resilience to a whole range of environmental hazards worldwide?
The potential seems enormous. Applying this kind of thinking, structure-aware, physics-informed, causally driven AI to other complex physical systems, yeah, that's definitely something to watch.
Indeed it is. We'll see you next time for the next deep dive.